And today we are going to discuss section 2.2, which is about limits. The notation of limit is very important for the calculus because a lot of concepts based on this definition. Unfortunately, we will not discuss it in the whole description. We have no time and we don't need that accuracy to well define it, but we will see many examples at how to do that. So one of the application of the limit you have probably already have seen, it is to find the asymptote for some function. For example, if we have function y equals 1 over x, and we are looking for the horizontal asymptote. And we know when x getting larger, our y becomes smaller and smaller, so y goes to 0. Right? So, for example, when x is 2, then we get that y is 1 over 2. When x is 100, y is 1 over 100, and so on. So we see that y comes to 0, and the way to express it is to write it in the following form. Limit, this is short notation for the limit, of the function 1 over x, and when x goes to infinity, is equal to 0. Okay. It's not a good way to write something like this, that if you have function 1 over x, then what happens when x goes to infinity? Maybe you would like to write something like 1 over infinity, that it is 0. But this is not good notation for that, because infinity is not a number. So you should be accurate with that. And the right way to express it is use the notation of the limits. So instead of writing infinity, you should write that x approaches infinity. Yes. So it's not a number. Infinity is not a number, so it's not a good way to write something like 1 over infinity. Let's consider the following expression. Limit when x goes to 4, x squared over x plus 4. So how you should think about it? You should think that what happens with this expression when x approaches 4. And one way to do that, it's just look what at the numerical values. So suppose that x is 4.1, then you can substitute what is this value into your function and get that x squared over x plus 4 will be something like 2.1. And when x is 4.01, it will give you 2.01. And 4.001 will give you 2.001, and so on. So you see that on the top, our x is becoming closer to 4, while the bottom, the value of our function, is approaching 2. So in that sense, we can say that the limit when x goes to 4 of our function x squared over x plus 4 should be equal to 2. in some sense, you may ask why we just not substitute x equals 4 into our function. So why we didn't write something like this. Limits when x goes to 4, x square over x plus 4 as just 4 square over 4 plus 4, which is 16 over 8, which is just 2. And in fact, in this case, it is right, but we will see that it's not always true when you can just substitute the value of x into your function and get the limit, because sometimes you may get the discontinuous function. That's what we'll discuss at the end of our class, and then it will not be true. So in general, so it's kind of remark, it's not true limit f of x when x goes to some point a is not always equal to the value of the function at that point. But it happens quite often. And basically, all functions that you will see in this course are continuous. So in fact, you can do that. But just a moment, we'll come to that. Okay, and another way to find the limit of the function is to draw the graph. So let's consider again y equals x squared x plus 4. And if you draw the graph of this function, it will look like this. And at point 4, so you see that x will go to 4. So it will be here, then here, then here, then here, and then finally approach the 4, sorry, and the value will be 2. So that's what we did, right? we calculated some, we chose some points x, which is near the point 4, say 4.1, say it's this point. Then we choose 4.01. Oh, sorry, it should be from the other side then. So it's not, some sense we did it from the right. If we looking at the tab, then we'll get that we did something 4.1 somewhere here, point somewhere here. We calculated the value of our function, then we calculated 4.01, which is somewhere here, then 4.001, which is somewhere here, and so on, and see what happens with the value. So what I wanted to say that you can also find the limit looking at the graph. But as I said, sometimes it's not that easy just to read the function at the given point. And for example, let's consider the following function: y equals sine of x divided by x. And let's say that we are interested in the limit when x goes to 0 of this function. So if we try to substitute naively x equals 0, then what we'll get? We'll get something like sine of 0 divided by 0. But sine of 0 is 0 itself, so we get something like 0 over 0. And it is in determinate form. I don't know what it is. It can be anything that we will learn when we'll study L'Hopital rule. And I don't remember what is. It will be after the derivatives. It will be section 6.9. And when we will study that, we will see that this expression 0 over 0, or sometimes it's infinity over infinity, can be anything. It can be finite number like square root of 3, or it can be infinite number like minus infinity, or sometimes it will not be defined at all. But still, nevertheless, we cannot calculate it, but nevertheless, we can find the limits, because again, if we just substitute, just create our table and evaluate our function at some points near the 0, then we will see that, say, at point 0.5, our function will have the following value. While at point 0.25, we'll get 0.9896. At point 0.2, we'll get 0.003, and so on. So we see that while the x is approaching 0, our function gets closer to 1. So in that sense, we can write down that the limit when x goes to 0 of our function sine of x divided by x is equal to 1. Okay, and even more, this initial function is not defined at 0 because it is 0 of the denominator, and we know that the domain of the function shouldn't include x equals 0. But still, there is a sense to consider the limit of this function, because we are not interested in a value of our function at this point, but rather interested what happens near this point. And this is kind of motivation for the following definition of the limit. So suppose we have our function f of x, and this function becomes arbitrarily close to the number L. As x approaches A. So arbitrary close means that f of x goes to L, and as x approaches A means that x goes to A. Then we say that the limit of f of x when x approaches A is equal to L. And this A can be not even finite number. That's also kind of remark. A can be infinity and minus infinity as well. Because as we have seen in our first example, when we considered 1 over x, oh, sorry. No, not considered, but if we consider for our initial function 1 over x, and interested what happens when x, no, it was our first example, sorry. So it becomes larger. We said that it becomes larger, but yeah. That means that x goes to infinity. So this definition also covers the case when x approaches to infinity and minus infinity. Of course, sometimes the function may have no limit. For example, what can be the example? What can be the simple example? Okay, let's consider the function that is defined only for natural numbers, f of n, which is -1 to the power n. And so what happens? Our function will have, at point 1, it will be -1. At point 2, it will be 2. Oh, sorry, 1 again. At point 3, it will be -1 again, and so on. So it continued jumps from -1 to 1. And there is no limit when n goes to infinity of our function f of n. Because it's not 1, because after a while it will jump to 1, to -1, and it's not -1 because on the next step it will jump to 1. So this limit doesn't exist. Okay. Sometimes, but it's not covered in the textbook, but that's what surprised me. Sometimes you can get that the limit is infinity. For example, what is the limit of x when x goes to infinity? It should be infinity itself, right? And another example, what happens when x goes to 0, let's say, no, let's discuss slightly later. So that means that L, the limit can, in this case, we call that there is no finite limit. Some textbooks say that there is no limit also, but in some sense it's infinity. It just depends on your notation or convenience. But what I wanted to say that sometimes it can be infinity as well. Let's do example with this function. What happens with this limit when x approaches -2 and the function is x to the power 2 minus 4 divided by x plus 2. Again, if you naively substitute it, then you'll get something like -2 squared minus 4 divided by -2 plus 2, which is again 0 over 0. And again, you don't know what it is, so that means that you need to investigate it more accurately. And the way to do that, you should play a little bit with your function itself. So let's write our function x squared minus 4 over x plus 2 using the difference of squares. So it is the same as x minus 2 times x plus 2 divided by x plus 2. And then we see that there is a cancellation of two factors, and we get that it is x minus 2. And then we can say that our limit when x goes to -4 of this function over x plus 2 is the same as the limit when x goes to -4 of x minus 2. Right? We just canceled some factors and get that it is -2. But now I can put I can see that when x goes closer to -4, this expression gets closer to -6. So the limit is -6. Oh, I started with -2 and ended with -4. Sorry about that. Let's do it there is no sense for -2. Okay. Okay. -2. -2, -2. Okay, and another
How did you get
yes,
-6 with that again?
yeah. If I change it to -2, indeed it will be -4. Thank you. Let's do another example. Say limit when x goes to 3, 9 minus x squared over x minus 3. And again, if you naively substitute, you will get 9 minus 9 over 3 minus 3, which is 0 over 0. But again, you can factor it out and see some cancellation. So it's 3 minus x times 3 plus x divided by x minus 3 when x goes to 3. And there is a cancellation, but first you should notice that x minus 3 is the same as minus x minus 3. And then it's indeed straightforward cancellation with the denominator, and we get that it is the same as the limit of minus 3 plus x when x goes to 3. But when x goes to 3, 3 plus x approach 6, and thus I get minus 6. Okay? And and let's see what happens with the graph of this function. So again, if we do the same cancellation, we see that our function is the same as a function. So right. So 9 minus x squared over x minus 3. First of all, what is the domain of our function? The domain is all x except 3, all real numbers except 3, because 3 is the 0 of the denominator. So at point 3, our function shouldn't be defined. But outside this point, we see that this function is the same as minus 3 minus x. And this is just a straight line that goes like this. And again, we should exclude this point from our graph, because this is a point 3 and minus 6. That's what we found. And you see that there is no value of our function at this point, but when we approach from the left and from the right, that's what we'll do in a moment, our limit will be minus 6. Yeah. So again, the function is not defined at this point, but we found that the limit is minus 6. And indeed, we can approach this whole from two sides, from up and from the downside and downside. And this is kind of motivation for the following limits. Limit when x goes to a plus f of x equals L. So plus sometimes it is also denoted as limit f of x goes to a plus 0. That means that you approach this point from the right. So if you have, this is your x, this is your a, so you're approaching something a plus small number, so you're approaching from this side. And the same story happens when you consider the limit f of x when x goes to a minus. Oh, sometimes you can see that it's limit f of x when x goes to a minus 0. So minus 0 is of course nothing, but it's just the notation that shows that you should approach the point A from the left. So it's something slightly smaller than A, somewhere here. Okay, and for example, let's consider this function limit when x goes to 2 plus square root of x minus 2. So why we consider this limit? Why not x goes to 2? Because when we saying that x goes to 2, we do not specify from which side, while the function is defined only for x that is equal or greater than 2, right? So we cannot approach it from the left. That means that we have only one option to approach it from the right. And still, again, you can calculate what happens with the value of your function and get that it will be 0. Okay. So it's indeed sometimes it depends from which side do you approach. And you'll see the example when the limit from the left-hand side is not the same as the limit from the right-hand side. And that's the situation when the function is discontinuous. But before that, let's consider another example when x goes to infinity. And we have the following ratio, 3x squared plus x plus 1 over 2x squared minus x plus 2. Again, what we can see? We can see that when x becomes large, our denominator is large and our numerator is large. So it's not clear what happens with this ratio. And there is a trick that probably you have seen when you calculate the horizontal asymptote, when you divide both numerators and denominators by the highest power of x. So let's divide the numerator and numerator by x squared. Then we can write down that this limit is the same as the limit when x goes to infinity, 3 plus 1 over x plus 1 over x squared. So I divide by x squared. And in the denominator we get 2 minus 1 over x plus 2 over x squared. And then what you can see that 1 over x squared, when x goes to infinity, goes to 0, right? It's similar to 1 over x, that's what we discussed at the beginning of the class, but this approaches to 0 even faster. Because when x is, say, 100, then it will be 1 over 100 squared. And the same story happened in the denominator. This goes to 0, and this goes to 0. And finally, what you get, what is left is just 3 over 2. Okay? You can also think what happens if you have something like 3x cubed plus 2 over x squared plus 1 when x goes to, say, minus infinity. Then, if you do the same trick, divide by the highest degree of x, which is x cubed, you'll get 3 plus, I should write the limit, limit when x goes to minus infinity, 3 plus 2 over 1 over x, sorry, 2 over x cubed plus 1 over x cubed. So this goes to 0. This goes to 0, but also this goes to 0. So it's slightly tricky. And so we get 3, something like 3 over 0.
How do you know it goes to 0 again?
So that's what we did in the beginning, right? So we discussed that the limit, we discussed when x goes to infinity, right? 1 over x, what happens with this expression, that this is 0, right? But where the same story happens when x goes to minus infinity, right? That it's also 0, it's small negative number. In this case, it was small positive number, but in this case, it's small negative number. And if you look at the graph of your function, so if you graph the hyperbola, you will see that it looks like this, right? And for the negative, it looks like this. And you see what happens with when x goes to plus infinity, you see that the value of y is going to 0. And the same happens when x goes to minus infinity, the y value also goes to 0, but from the below. Okay?
Okay.
Yeah, that's what happens with these two. But 3 over 0, it's again something strange. And in this case, what you should do is to divide it not by x cubed, but by x squared. So we get that it is the same as the limit 3x plus 2 over x squared divided by 1 plus 1 over x squared. So sometimes you should play with the expression to figure out what's happening.
So we don't always use the highest degree polynomial?
Here's the trick. That's what we can do in general. When you see that the degree of the numerator and denominator is the same, like in this example that we did, then you should divide indeed by the highest, and that will give you the right answer. If one of the degree of denominator or degree of the numerator is bigger than another, then it's either 0 or infinity. That's what we'll see in this case. Just in a moment. So in this case, if I divide by x squared, this goes to 0, this goes to 0, and I get that it is the same as the limit of 3x when x goes to minus infinity. But it is the same when x goes to minus infinity, 3x goes to minus infinity as well. And the point that I wanted to mention that if you have a ratio of two polynomials, and then you have three options. Degree of f is equal to degree of g. And in this case, you indeed divide by the highest degree, numerator and denominator. And that will give you the answer. That's what we have seen here. If, say, degree of f is greater, and you are considering limit when x goes to, say, infinity, degree of f is greater than degree of g. So in some sense, that means that the numerator is greater than the denominator at the infinity. Then you will get that it is infinity. That's what we have seen here. We considered minus infinity, but for the infinity, it will be the same. And in other case, when degree of f is less than degree of g, so in this case, denominator is greater than numerator, then your limit will be 0. And here's example for consider limit of 3x plus 2 divided by x squared minus 1 when x goes to, say, infinity. Then you divide by x, and you get limit. Yes, in these two cases, you divide by the smallest one. Smallest degree of these two. Then you get the limits of 3 plus 2 over x divided by x minus 1 over x. And again, this goes to 0, this goes to 0, and you get that it is degree, the same as the limit when x goes to infinity, 3 over x. But 3 over x, when x goes to infinity, it's similar to 1 over x, and it approaches 0. Okay? Basically, in this textbook, you will see, I think, only the first case when degree of f is equal to degree of g, at least in this section. I think in the L'Hopital rule, it will even prove this kind of theorem that if you have a ratio of two polynomials and if degree of one is greater than degree of another, then the limit when x goes to plus minus infinity will be either 0 or plus minus infinity. Depends on the situation that we discussed. But what why I wanted to mention it, that sometimes, I mean, it's not hard to see what happens if they are not equal. You just need to, again, divide it, but not by the highest, but by the smallest one. Smallest between the two degrees of numerator and denominator. Okay. And here's a very helpful theorem that says that suppose you have two functions. And suppose that the limit of the first function when x approaches a is L, while the limit of the second function is M. Then you can say what is the limit of the difference and of their sum. It will be just the sum or difference of the limit values. This is first theorem. The same happens with the product. When x goes to a, f of x times g of x, it will be just L times M. And the same happens with the ratio, except there is a small problem, of course, when the limit of g is 0. But if it's not 0, then there is no problem at all. It's L over M, but in case when M is not 0. In case when it's 0, you should investigate it more accurately. And the last one, that if you multiply your function by some constant, then the limit will be multiplied by the same constant. And important thing here that these two limits should be finite. Better to say finite because they cannot be minus infinity as well. Okay, otherwise you will get something strange. For example, L and M should be finite. Otherwise, let's consider, say, function f is x and function g is also x. Then the limit of their difference, say limit of f minus g, so limit when x goes to infinity of x is of course infinity. And then the limit of f minus g is, if you try to apply this, it will be infinity minus infinity. And again, it's not clear what it is, because it can be minus infinity, it can be plus infinity, or it can be not defined again. So in this case, of course, this limit should be 0. If you just do it separately, x minus x is the same as the limit of 0, and it's 0. So you should be accurate when you get infinity minus infinity or infinity divided by infinity and stuff like that. Okay. So when you get something strange, that means that you probably did something not very accurately, and you should check your calculations. So either you get something like infinity minus infinity, or in this example where we discussed, where is sine of x? Sine of x divided by x, so it's 0 over 0. It's not also clear what is the value of this stuff. So you should do it somehow in a different way. Okay, so in this theorem, it's important that both limits are finite. Otherwise, you cannot apply this theorem. Okay, and now about when we can plug and when we cannot plug the value of x into the function to obtain the limit. And it's called continuous and discontinuous functions. So before that, let's consider the following function f of x that will take values 0 and 1. It will be 0 when x is less than 0, and it will be 1 when x is greater than 0. It is piecewise function. That's what we discussed. That's what I discussed without you, unfortunately, at the last 8 minutes of the previous class. And so if we graph this function, it will look like this. Our x, our y. So it's 0 here, including 0.0, and then it's 1, excluding 1 after that. And from this picture, we can say that the limit of our function, limit f of x when x approaching 0 from the left, right, 0, 0 minus. So we are coming to 0 from this side, will be 0, right? So because I'm taking some values here, 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 and I still get 0. While the limit of the function when we approach from the right, so I'm here, 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 it seems to be 1, right? And we see that these two limits are not the same. So it's kind of jump from 0 to 1. And such jump is called discontinuity. And we also have seen another functions like y equals 1 over x has a jump, but in this case it's, so here the jump is finite, right? The jump is just 1 unit. While in this function 1 over x has an infinite jump. So again, it looks like this, and it looks like this. So limit when x goes to 0 from the left. So I'm here, 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 and my function is becoming large negative. So it's minus infinity. While if I'm approaching 0 from the right, so I'm somewhere here, and my value of function is becoming larger and larger, will be plus infinity. So we see that now the gap is infinite. So we have minus infinity and plus infinity. So if we come into 0 from the left, we get minus infinity, and if you come in from the right, we get plus infinity. So it is indeed again discontinuity, but in this case jump is infinite. In this book it's not discussed, but there are some types of discontinuity. So this example is discontinuity of the first type when it's finite. This is second type, and there is discontinuity that can be removed. This is kind of third type when it's like sine of x over x, because if this function is not defined for x equals 0, but if you look at the graph, you will see that the limit from the right and from the left is the same one. It just the function is not defined at this point. So in some sense, you can define by hands at this point by the making the value at 0 equals 1. So it's another type of discontinuity, but nevertheless, we are interested only just in discontinuity in general. And this is kind of motivation for the opposite situation when the function is continuous. So a function, say f is continuous at point x equals a if f is defined at point a and limit f of x going to a is equal to f of a. In some sense, it's tricky. I mean, that means that this should mean that both limits from the left and from the right should coincide. Oh, a plus should be the same as the limit when x goes to a minus, and should be f of a. And again, as I said, basically all functions that you will see are continuous, except some specific points. For example, the function, I don't know, x squared plus minus 1 yeah, I forgot to mention. So let me. So it's continuous, and so we define the continuity at some point. But also you can say that the function is if the function is continuous at all points of at all points in the interval, then we say that it is continuous on this interval. Okay. And yes, so for example, x cubed minus 2 divided by x minus, say, 1. And this function has only problem at x equals 1. It is discontinuous. But everywhere else, it is continuous. So it's continuous from minus infinity to 1 and from 1 to plus infinity. So that means that if you want to calculate, say, the limit when x goes to 2, x cubed minus 2 over x minus 1, by definition, this limit, and you know that this function is continuous at point 2, that's what we just discussed, you just can say that it is the same as the value of the function itself at this point. So it's 2 to the power 3 minus 2 over 2 minus 1. So it's 8 minus 2 divided by 1, which is 6. So again, almost all functions that you will see are continuous, though the way to check if it's continuous or not, you just can first plug the value and see if it is, you will get something strange or not. For example, if you try to calculate the following limit, x plus 3 over x minus 1, when x approaching to, say, 1, of course, you will get something like 4 over 0. And this is kind of strange. I mean, you're dividing by 0. That means that you cannot plug just 1. So in this case, we cannot use this definition. So in other words, we can say that x plus 3 over x minus 1 is, again, discontinuous at point x equal 1. While for all other points, if you calculate, say, x goes to 5, it is fine. 5 plus 3 over 5 minus 1, which is 8 over 4, which is 2. Okay, which is totally okay. So it's not a theorem how to check if it's continuous or discontinuous, but in all examples that you will have, it's quite helpful just to plug and see what happens. If everything is okay, that means that your function is continuous at this point. If you see something strange, or you divide it by 0, you get infinity, then probably you should do it more carefully. Okay. Okay. Yes, another thing that I wanted to discuss is sometimes you have irrationality in your function, and you should do something with that. Where is this example? Strange. I think I have seen it. Just a moment. No. Okay, let's do the following example. Say you have a limit when x goes to infinity, say x minus square root of 2x minus 4x squared plus 3. Then, again, if you just try to plug it, you get infinity minus infinity, so nothing very interesting, and you cannot say anything about that. But it also, in some sense, we haven't discussed how to do that, how to treat the irrationality. And the way to do that is to multiply by the conjugate expression. And by the conjugate, I mean the following. You should multiply by the same stuff, but with plus. And why you need to do that? Because now you can use again the difference of squares formula and see that it is the same as the limit when x goes to infinity, 2x squared minus square root of 4x squared plus 3 squared, right? And now you see why we use this trick, because now I have square root and it's squared, so I get just that it is the same as the limit when x goes to infinity, 4x squared minus 4x squared plus 3. And I see some cancellations, and the final answer will be minus 3. Okay, so get rid of irrationality. And of course, you can do the same trick when it is in the denominator. Oh, of course, yeah, pardon. I did stupid thing. Of course, I can multiply, but I have to divide it. Sorry. It's easy, but not that easy. So I multiply, and of course, I need to divide by the same expression, 2x plus square root of 4x squared plus 3. And so I get this divided by 2x plus square root of 4x squared plus 3. So on the top I have indeed cancellations, but still I have something on the bottom. So I get that it is the same as limit. Okay, correct. Check. So I have this, I multiply and divide by this, and then I have indeed this. Okay. Yes, and then I get that it is the limit minus 3 over 2x plus square root of 4x squared plus 3 when x goes to infinity. But what we see that the numerator is constant while the denominator is increasing and it's becoming larger and larger. That means that my limit will be just 0. Okay. Yes, so my mistake was that when you multiply by something, you should divide by the same expression if you want equality sign here. Otherwise, you just obtain something different. Okay. Okay. What else I wanted to say? what else I wanted to say? And yeah, that's what I want to say. That of course you can do the same trick, but when such irrationality is in the denominator, denominator, yes, square root of, say, x plus 2 minus x when x goes to infinity. So you get, again, if you naively plug infinity, you'll get 1 over infinity minus infinity. It's not clear what it is. And let's even do, say, here x. So it will be slightly more interesting. So again, when you see irrationality, you should rather get rid of that. But also, okay, two ways. One way to multiply again by conjugate. So you might multiply by square root of x plus 2 plus x, and I divide by the same square root of x plus 2 plus x. And here is my square root of x plus 2 minus x. So, and x goes to infinity. And then you get limit when x goes to infinity, x times the same stuff, x plus 2, let's keep it for a while, divided by. And on the bottom, again, the difference of squares. First is x plus 2 and minus x squared, right? And so finally I get that it is the limit when x goes to infinity. And now I can divide, no. Now I can multiply term by term, so I get x squared on the top plus x times square root of x plus 2 divided by minus x squared plus x and plus 2. And so far it's still unclear because now we get infinity divided by infinity. So in some sense it's not better than the initial one. But now at least we have no irrationality in the denominator. In some sense it's better. And what is the next step? The next step is again trying to understand what are the powers. So again, the power of the numerator is x squared, and x times something that has power 1/2. So this is something that x to the power 3/2. And the denominator is again the highest is x squared. So we see that the highest power is still x squared. So let's divide by x squared. And then we'll get that it is the limit when x goes to infinity. 1 plus 1x is cancelled, so I get square root of x plus 2 divided by x. And here I get minus 1 plus 1 over x plus 2 over x squared. So with the bottom, we know what to do. This goes to 0. This goes to 0. With this one, you should be slightly more careful. So you can rewrite it as x plus 2 over x squared. So it's everything under the square root. And this is the same as 1 over x 1 over x plus 2 over x squared. But nevertheless, this goes to 0 when x goes to infinity, and this goes to 0. So you get 0 plus 0. So we get that it's the same as the limit 1 over minus 1, which is minus 1. So this is one way to solve it. Multiply by the conjugate part and get rid of irrationality, and then again use the trick with the highest power, divide by highest power denominator and numerator. But you can do it maybe faster if you do the following. So let's consider this again. You can divide by, again, if you look at this thing, this is x to the power 1, this is x to the power 1, while this is something like x to the power 1/2. I mean, something like, because it's square root of x plus 2, but if you think about the power of x, it is x to the power 1/2. So still, the highest power is x to the power 1, so let's divide by x. And then you'll get that this is the same as the limit when x goes to infinity, 1 over square root of x plus 2 divided by x minus 1. And you already have seen what to do with this stuff. You put x under the square root and get x plus 2 over x squared. And this is square root of 1 over x plus 2 over x squared. And this, again, goes to 0, and this goes to 0 when x goes to infinity. And we get, of course, the same answer, 1 over minus 1, which is minus 1. So what is the point of all these calculations? The point is that, so kind of summary. That if you have a limit, and okay, let me say it by words, long to write. So if you want to evaluate the limit, first thing you should check if the function is continuous or not. Again, in many cases in this textbook, the function is continuous except some specific points, like zeros of the denominators, or something like square root is not defined for negative values and stuff like that. If you understand that the function is continuous at this point where you want to evaluate it, then just plug the value and that will give you the answer. If you plug the number and you get something strange like 0 over 0 or infinity over infinity or 0 minus 0 or whatever, infinity minus infinity, then probably you need to do it more carefully. And how to do, what are the tools to do that? So either you need to factorize numerator and the denominator in your ratio, or you should get rid of irrationality, that's what we did here. Or sometimes, what else can happen? Sometimes you need to consider the one-side limits. What happens when x approaches the falling point from left side or right side, because it can be different, and stuff like that. So in many cases, again, you can just plug and get the answer. In other cases, you just need to play with the expression itself. And some tricks that you can do, I have shown you today.